So welcome back to the chemistry videos, everybody. I hope you're all doing well and staying safe and healthy. Our first video this week will be a review of last week's material. And as you recall, we're going to break chapter 14 up into 3 sections instead of 2 as we normally do. Because you're learning at home, we don't have as much interaction, and it's a longer, maybe more difficult chapter. So just to review, last week we started our discussion by talking about enthalpy, okay? And enthalpy measures the potential energy in a system. Okay, so it's a way of measuring energy, and specifically potential energy. Now, it's really hard just to get a grip on what the enthalpy is of a system, but it's much easier for us to calculate the change in enthalpy. And sorry, enthalpy is an H. We're going to talk about S's this week. So enthalpy is abbreviated with an H. Okay, so it's much easier for us to talk about enthalpy in terms of change in enthalpy. And the change in enthalpy is the energy change that happens in either a physical or a chemical change. Okay, so either a physical or a chemical change. So if we think about this in energy, if our change in enthalpy is negative, what does that mean? Okay, well, that means we've lost some potential energy. All right, it means we've gained some kinetic energy. And altogether, that means that it's an exothermic reaction. Okay, so if delta H, the change in enthalpy, is negative, that means our potential energy, remember, whenever we calculate a change, it's always the final minus the initial. So if this delta H is negative, that means our potential energy that we ended up with is less than the potential energy that we started with. So we lost some potential energy. Well, we can't just lose energy, it has to go somewhere. Well, it was converted to kinetic energy. And when we gain kinetic energy, that's an exothermic reaction. Okay, so a negative delta H is an exothermic reaction. And let's talk about it if delta H is positive. Well, that means our potential energy that we ended up with was greater than what we started with. So we actually gained potential energy and we lost some kinetic energy. And so that is an endothermic reaction. Okay, so these two are opposite of each other. We can't just lose energy. If we lose potential, that means we gain kinetic. If we gain potential, that means we lost some kinetic. Okay. Then we talked about how to calculate actual mathematical figures for these delta H's, and we talked about bond energies, and we learned that we could calculate delta H by taking all the energy required to break bonds and subtract all the energy to form bonds. Okay, and this would be one way of calculating the change in enthalpy. All right, and we can use this. We have tables that tell us these values for breaking and forming bonds, okay? And that's the table of bond energies. On page 420. So just as a form of review and maybe reinforcement to get our mind back in here. Let's look at comprehension check number 2. So I'm on page 422 if you're following along. So it wants us to use bond energies to determine the delta H for the following reaction, and then to determine if it's exothermic or endothermic. All right, so we have CO plus H2O yields CO2 plus H2, okay? So when we're using these bond energies, we have to look at the bonds of the reactants and the bonds of the products. So let's rewrite these using our Lewis diagram. Okay, so this CO, that's a little bit of a tricky one, all right? But the only way to make carbon and oxygen both happy is to have this triple bond here. That way oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Carbon also has 1, 2, 3, 4, 5, 6, 7, 8. So they're sharing these 6 in the middle. All right, and then we know that H2O, the Lewis diagram looks like that, and then that forms carbon dioxide. And hydrogen. Okay. So here, by drawing the Lewis diagrams, we see all the bonds that need to be broken and all the bonds that need to be formed. So this bond we need to break. This bond we need to break. And this bond we need to break. Okay, we need to break 3 bonds. The triple bond between the carbon and oxygen, and then the single bonds here. On this side, we need to form both of these bonds and then form this bond. Okay, so we're breaking 3 bonds, we're forming 3 bonds. All right, so we can go back to our equation here, and our delta H says all the energy required to break the bonds. So we can look at our table of bond energies on page 420. And to break a triple bond between carbon and oxygen, it's way at the bottom right-hand corner. That takes 1,072 kilojoules per mole to break that bond. Okay, then I have 2 of these single bonds between hydrogen and oxygen. So hydrogen and oxygen, if I look on my table, a single bond, those are 460 each. Okay, so I'm adding together all of these. Okay, so these are the ones I'm breaking. And then I'm going to subtract the bonds that I'm forming. All right, I need to form 2 double bonds between carbon and oxygen. So looking back on my table, that's in the 3rd column. Each of those is 732. Okay, and then a single bond between my H's. That doesn't take very much energy, 436. It's the first entry on the table. Okay, and I'm subtracting all of these. So I'm going to distribute this minus sign all through here. Okay, so the bonds I'm breaking, the bonds I'm forming. All right, so if I add all these up, what do I get here? Well, if I do all the math, I get 92 kilojoules. Now what happens to this over mole? Well, the way we're writing these, we could have said we had 2 moles of these bonds, but because I wrote them individually, each of these bonds is considered just a mole. So these are all just going to cancel. All right. If we look at significant figures carefully, because 460 does not have a significant figure in the ones place, we would actually need to round 92 to 90 kilojoules because we're adding. And the most precise we can get is the tenths position. Okay, so you take all of the bonds that need to be broken and subtract from those bond energies all the bonds that need to be formed, and that will give us a value for delta H. Okay, oh, and then the last part of this. So delta H is positive. So what does that tell us? Well, if it's positive, it gained potential energy. If it gained potential energy, that means it's an endothermic reaction. Okay? So that's comprehension check 2, talking about bond energies. Hopefully that shows you a little bit how to do those problems. Okay, then we moved on and we started talking about the standard enthalpy of formation. And if you remember, this was abbreviated delta H, had this little F down here for formation and this little degree sign. Okay, so what does all that mean? Well, the degree sign indicates that these values are only valid at room temperature. But don't worry, you'll only be given problems where we have room temperature, so that's not something you need to worry about. The standard enthalpy of formation also takes phase into account. Okay, because we know that a gas has more energy in it than a liquid, and a liquid has more energy in it than a solid. Remember, in a gas, the molecules are moving very fast. In a liquid, they're moving freely, but a little bit slower. And in a solid, they're just vibrating. They're not even free to move around. So that those gaseous molecules moving fast have more energy than a solid whose molecules are just able to vibrate. Okay. Another thing we know about this is that any element in its natural phase that the standard enthalpy of formation equals 0. Okay, so an example of this would be like O2 gas. Okay, oxygen gas exists like this in its natural phase. Hydrogen gas would be another example. All right, so any element in its natural phase, and these are probably the ones you're going to see most often, its standard enthalpy of formation is 0. Okay, so how do we use all these in an equation to calculate energy? Well, we use something called Hess's law, and in your book we see it written like this. Okay, so I have so many moles of molecule A plus so many moles of molecule B, these are my reactants, produce so many moles of molecule C plus so many moles of molecule D. These are my products. So this is just the lowercase letters indicate number of moles, and the uppercase letters are the actual molecule. Okay, so it's just a way to generically try to illustrate a chemical equation. Okay, so then if we use that to calculate delta H, what we learn is that delta H is equal to the products, so little c, the number of moles, times the standard enthalpy of formation of that molecule, okay, plus the number of moles of the other product times the standard enthalpy of formation time of that molecule, and then we subtract the products. So it's a little bit opposite of the bond energies. Okay, so the bond energies, we're breaking the bonds of the reactants and forming the bonds here. So we're taking these minus these, and in Hess's law, we're starting with the products and then subtracting the reactants. So we would subtract the number of moles of A times the standard enthalpy of formation of molecule A, and subtract the number of moles of B times the standard enthalpy of formation of molecule B. Okay? So, we're basically taking the products here minus the reactants. Okay? And for each of these, the number of moles times the standard enthalpy of formation. So let's look at an example. Comprehension check 3. And I feel like I'm not explaining this very well. The reason we're subtracting the reactants is because these are the standard enthalpies of formation. Okay, so to form the products, we can take the enthalpies as they are. To break down these reactants, we have to do the opposite of the formation, and that's why we subtract the standard enthalpies of formation, because when we subtract them, we're doing the opposite of formation, which is kind of breaking them down. Okay, so comprehension check 3. Is on page 426. Okay, so it wants us to use Hess's law to determine the delta H for the following reaction at 25 degrees Celsius. Again, 25 degrees Celsius is room temperature. Okay, so we don't need to worry about the temperature. We can use Hess's law, and it actually tells us to use Hess's law. So the reaction is HCl. And remember, in Hess's law, it takes into account, or the standard enthalpy of formation takes into account the phase. Okay, so we have this in its gaseous phase, plus NH3 in its gaseous phase yields NH4Cl. And that's in a solid phase. So this is kind of odd. We're adding two gases and we're getting a solid. So what is the delta H of this equation? Okay, well, let's go back. It wants us to use Hess's law. Okay, so according to this, Hess's law, this would be our A's, this would be our B, and this would be our C. We only have three things. We don't have two products, so we don't have a D in this case, all right? And look at this equation. All of the little lowercase numbers are 1. We have 1 mole of HCl, 1 mole of NH3, 1 mole of NH4Cl. We don't have any coefficients in front of these indicating we have more than 1 mole. Okay? So Hess's law says start with our products. Okay, we don't have a D, so we'll start with C. Okay, we have 1 mole of that times the standard enthalpy of formation of NH4Cl solid. So let's look at our table of standard enthalpies of formation on page 424. And he won't give you a molecule that's not in this table. So NH4Cl solid, it's almost the last one. It's the second to the last, all right? And it's negative 314.6. And again, it's kilojoules per mole. Okay, so we had 1 mole because we had no coefficient in front, times the standard enthalpy of formation for this as a solid. So I went to my table and got this value. Okay, so that's my C. I don't have a D, so I'm not going to worry about D. Now I'm going to subtract my A. All right, again, here's my A molecule. I only have 1 mole of it. I don't have a coefficient in front, so the 1 is understood. Okay, 1 mole of HCl gas. So the standard enthalpy of formation of HCl gas, it's in the 3rd column. It's minus 92.3 kilojoules per mole. All right, so that takes care, we didn't have a D, that takes care of my A. Now I'm going to subtract my other reactant, B. Again, 1 mole NH3 gas. If I look in the table, NH3 gas is in the middle of the 3rd column, negative 45.9 kilojoule per mole. Okay. You can see here my moles are going to cancel out, my units are going to cancel out. Okay. And if I do out this multiplication, 1 times negative 314.6 is negative 314.6 kilojoule. Now here I have a negative times a negative, so this is now going to become positive 92.3 kilojoule. And then the same thing here, negative times a negative. So this will become positive 45.9 kilojoule. All right, and if I add all those things together, what do I get? Negative 176.4 kilojoule. Okay. Again, we're solving for delta H. Delta H is negative, so I know then that this is an exothermic reaction. Okay. All right, so this one was pretty easy because there were no coefficients in front. So let's look at comprehension check 4, where we actually have coefficients in front, and he doesn't even give us the complete equation. He just says he wants the complete combustion of C2H6 gas. So C2H6 gas, well, we know for combustion we need oxygen gas, and we know that that will yield carbon dioxide gas and water vapor. Okay, if it's the complete combustion. So all of these are gaseous. All right, is this equation balanced? So I have 2 C's here, only 1 here, 6 H's, only 2, so it's clear this isn't balanced, okay? So if you would take the time to balance all this, you're gonna see that we need 2 of these molecules, we need 7 oxygen molecules, 4 carbon dioxide molecules, and 6 water molecules. And now this is a balanced chemical equation, okay? So a couple things you needed to remember before we could even start calculating our change in enthalpy. You needed to remember what complete combustion was. So that was adding oxygen to something and coming up with the products of carbon dioxide and water. Then you needed to remember to balance the equation, and only until we do that can we calculate delta H. So again, let's identify this 2 is our small a. Okay, this molecule is our uppercase A. This 7 is our small b, and O2 is our capital B. The 4 is our small c, CO2 molecule is our capital C. 6 is our lowercase d, and the H2O gas molecule is our uppercase D. So here I'm just trying to show you how this equation can relate back to the generic Hess's law. Okay. So Hess's law then tells us if we have an equation like this to calculate delta H, what do? Well, we take our little c, so that's 4 moles, times the formation of our capital C, which is CO2 gas. So if we look in our table, CO2 gas has a negative 393.5 kilojoule per mole. All right. Hess's law says then we add our other product. So our lowercase d tells us there's 6 moles of H2O gas. The standard enthalpy of formation of our H2O gas is negative 241.8 kilojoules per mole. Okay, the next thing I do is I start looking at my reactants. I subtract my A's, so I have 2 moles of A. My standard enthalpy of formation for C2H6 gas. If I look at my table, it's the second entry, minus 84.7 kilojoule per mole. And then finally, I have to also subtract my B. I have 7 moles of O2 gas. Look at my table. Oh, O2 gas isn't in my table. Why not? Well, remember, any element in its natural phase, the standard enthalpy of formation is 0. Well, O2 is how oxygen exists in its natural phase, so this is just 0. All right, so this all just goes away. Okay. So what do I end up here with? If I do my 4 times my minus 393.5, I end up with negative 1,574.0 kilojoules. Again, my moles cancel out. Okay, here I have a plus times a minus, so that's going to be minus. If I do the math, 1450.8 kilojoules. Again, my moles cancel out. Here I have a minus times a minus, so this is going to be plus. 2 times 84.7 is 169.4 kilojoules. And if I add all those together, I end up with 2,855.4 kilojoules. Is my delta H. Delta H here is positive, so what does that tell us? A positive delta H means that it's endothermic. Sorry, I think I made a mistake here. This must be negative. I think that's wrong on my notes. So this is exothermic. Sorry about that. Hopefully this math is working out. Negative 2855.4 kilojoules. I didn't see my negative. Okay. So hopefully that helps you understand what we did last week, that's a good review for you. Again, if you have any questions, I'm sorry I haven't been checking Google Classroom probably as much as I should be. I need to get in the habit of doing that, but please let me know if it's something that you think could benefit everybody. Put your question out there, and hopefully this helps solidify things from last week. So the next video will be on new material in chapter 14.